Hey engineers, and welcome to 2.2, which is a unit on materials. So this whole unit, we're going to be talking about materials science. What makes materials beneficial to us? I remember when I was touring the NASA Johnson space down in Houston, Texas, at the space materials. Anytime any asteroid or any cometary dust or all the moon rocks, they're all housed in this one building. And I remember, and this guy that was giving us a tour, we asked him, like, what are you excited about when you bring back like something from space? And he said, I love testing it to see what the material properties are, because maybe it's something cool we don't even know that could work and solve so many problems. So I was really taken aback by that, by like, oh, when they get a new object, what is it like? Tell me about its hardness. Tell me about how the color of it. Tell me about its ductility. Tell me about its strength. Tell me about, there's a million different things that material properties, and that's what we're going to be talking about throughout this chapter. And I thought, I'm watching a video right now, a video series by a guy. His name is Martin, and he's building this marble machine, and he's trying to make a device that when you crank it, it drops marbles onto a bunch of different instruments. And right now he's making what's called a marble divider. So like
into a full scale.
Marbles roll down and they go into different tubes, which will end up dropping on the different instruments. So what he's doing in this video is he originally made it out of wood, and now he's thinking, maybe I want to make it out of this different type of plastic. So he's machining this with his CNC router.
And it machines nicely, and it starts to shine after some time. So
right there, a couple of material properties. It's how easy is it to machine? What does it look like after it's done?
I get super excited, and this is the final result. It's so cool. So the latest generation, the POM version.
So he has one that's 3D printed, that he used 3D printing, and then he had he's calling it POM. I'm sure it stands for something like polyethylene something. And then he has a plywood that he's made. So he's trying to test 3 different materials to see which one is going to give him the best results.
And see which one performs best.
Ultimate material showdown. It's the ultimate material now. Who will win? Ultimate material showdown.
So suffice to say, he ends up doing a bunch of tests at different angles. He has this little angle finder that he rolls the marbles down to see how well they flow past one another without getting hung up because of the machining.
Flawless. Release that marble super slow.
And he can adjust the pitch of this, like how much it's tilted, and then he can tilt it left and right too, so he can. So he's showing, like, right there with the wood, it kind of got hung up at this angle, and he's using the same angle with that POM, and they're sliding past each other pretty easily. And then he's got his 3D printed version over here at the same angle, getting hung up right there. So he comes to the conclusion that this is the best material for him in his design. So let's talk about materials and fill in some of our notes. Materials, they're just a substance that we make stuff out of. Everything that you buy or everything that you own is made out of a material. And that material was meticulously debated by some people to figure out how does it feel, like what's its durability, how easy is it to manufacture, how easy is it to machine. There's a lot of different things and a lot of different criteria that go into building something. This website, MatWeb, it lists over 76,000 individual unique materials, and it lists off their different aspects, physical properties, material type. We can go searches, carbon, ceramic, fluid, metal, other engineering, polymers, pure elements, wood, and natural products. There's, 10,000 different ceramics? Throughout history, cultures have been defined by their ability. Maybe you've heard of the Bronze Age. Maybe you've heard of the Stone Age because of their use of the different type of material. What would you say the age that we're in right now? Like, people millennia from now will look back at this age and be like, oh, that was the plastic age, where people polluted the entire planet and their bodies with different plastics. Materials continue to change the world. Advancements in materials create and continue advancement possibilities for each sector. So when we build something new, find something new that we can apply that to something, it's a self-feeding circle. The simplest material, and you saw that, was elemental. So something like hydrogen, carbon. You can't break it down into something else. The elements themselves are divided into categories, 3 categories, based their physical properties, their chemical properties. What's their boiling point, their melting point? How dense are they? What color? How hard? Their texture? Do they react to acid, oxygen, salt water? Metals, nonmetals, and metalloids. So hydrogen that I said before, definitely a nonmetal. Copper, metal. Metalloids, we'll talk about those. What makes a metal? They're good conductors of heat and electricity in general. They're hard, shiny, reflect light. They're malleable, meaning that you can shape them into different places. Ductile, they're stretchable. And they typically have 1 to 3 valence electrons, which makes them good conductors of electricity. That valence electrons we talked about with electricity. Nonmetals, they're mostly gases at room temperature. The solids are dull, brittle, and powdery. I'm trying to think of something like potassium, very brittle if you've ever had an experience with that. They're poor conductors of heat and electricity. Here's glass, neon. Metalloids, they possess both metallic and non-metallic properties like silicon. That's a good example of a metalloid. Compounds, things that you combine to make 2 or more things. For instance, the rubber. Or maybe it could be aluminum, or it could be something like an alloy, that bike frame. Compounds, elements, combinations are not random, but they're based on specific mass ratios, like water, 2 parts of hydrogen to 1 part of oxygen. Compounds can only be broken down through chemical process, not physical process. Like a cookie, for instance. You could physically separate out, or soup, you could separate out the carrots and the celery and the noodles. You don't need to chemically break that down. A mixture. A non-chemical combination of any 2 or more substances. So, like concrete is a really good example of a mixture. You have rocks of different sizes with a cement in between there to hold those together. And then you even put like metal in there for reinforcement for tensile purposes. Material classification. They're based on material composition and distinguishable properties. Common material classification categories. Metallic materials, ceramics, organic materials, polymeric materials, composite materials. Metal, steel, ceramic, glass, organic, paper, polymeric, plastic, composite, fiberglass, carbon fiber. Metallic materials, they are pure metal elements not commonly found or used, except aluminum. Aluminum is a pure metal element that we use steel is not. You're combining, I can't exactly, I think it's carbon with, I'm not exactly sure what steel is. Thermoelectrical conductors, mechanical properties include strength and plasticity. Ceramics, they are really good insulators, both thermally and electrically. So they have this power line up here, and these things that insulate the power line from others, they use ceramics like glass or porcelain a lot of times. Here's a sink, porcelain, and then these thermal tiles on the bottom of spacecraft. They're really amazing properties. Here's a demonstration of just the power of ceramics. This is an insulating tile from like the space shuttle, and they put this in an oven at like 3,000 degrees. I'm talking, you put a pizza in at 3,000 degrees, and it's vapor. I mean, it is just, it's a cloud at that point. But you have these thermal tiles in there, and they come right out of that oven at 3,000 degrees, and he's going to grab that thing. He's just going to grab it right on the edges. They're so good at getting rid of heat that you can pick this thing up that's come out, just amazing properties inside of ceramics. High strength at high temperatures, but they're very brittle. You drop a toilet, it's going to shatter and break. Plates, clay, brick, tile, sewer pipes, chimney flues, china, porcelain. These thermal tiles. This is one of those tiles off of that space shuttle that you saw that person grabbing right there. Refractory, high temperature. That's the idea of it giving away. It's able to bounce heat off of it. Electrical, they're resistors, so you can, what they call dope them, you can use different mixtures to create certain amounts of resistance through a material. A thermistor, it regulates heat flow, so if it gets too hot, the hotter or colder, it adjusts its resistance accordingly. A rectifier, it's kind of like a diode, and then it only allows current to flow in one direction. Or heating elements for furnaces. Here's a spark plug. This thing has to go inside of an engine that is really high temperature. You're burning gasoline, so you need something that can withstand that heat but still separate a positive from a negative to create a spark, and those are made out of a ceramic. Organic materials, they were once living, mostly consist of carbon and hydrogen. Chalk is a really good example. It used to be seashells. All chalk at some point was the shell of a living creature that fell to the bottom of the ocean, and the ocean floor subducted that and compressed it into limestone. Then we make chalk out of it. They're genetically alterable, like genetically modified corn, renewable, sustainable. You can keep growing it. Distinguishing characteristics. They're mostly organic elements. Oh, these are polymers, so plastics. Let me go back to organics here. Paper, we mentioned that before. Food. And then cotton, silk, different materials that we can farm. Polymers, they're really light. They are flexible. You can make them flexible. You can make them, there's all sorts of plastics. You can make them very rigid. You can make them like rubber. So you can make them, they're not slippery. They're really sticky. Plastics, they're thermoplastics. You heat them. So you heat them up to make them expand or contract. You can blow mold these things. Some things you can remold, other things that you can't, like thermoset. Once you heat it and you make it into its shape, it's set. You can't change that. But then other things you can melt down and remold again. Thermoplastics, thermosetting. Elastomers, things that are very stretchy. Vulcanization is a way to make really stretchy things very durable. Without the vulcanization process, tires would not be possible. Composites. This is a boat. Fiberglass. So you're taking glass fibers, which are really good in tension, and you're putting them in all different directions, but you're hooking those together with a resin. Carbon fiber in bikes, and here's a carbon fiber sheet right here. Plywood is a really good example of a layer composite. So on plywood, the layers are alternating. The grain goes this way, that way, this way. They're at 90 degrees to one another, so that expansion that happens with the humidity change and temperature change, it really regulates that and doesn't allow it to do that. So it's a much more stable wood. Particulate composites, concrete, fiber reinforced, fiberglass, carbon fiber. When you pick your material, there's so many different things. Like, it needs to conduct electricity. I don't want it to conduct electricity. Maybe it needs to float. I need it to machine very easily. Oh, and I want to cast this in a mold. I want to 3D print it. What do you need? It all depends on what your project is. It depends on your budget. You know, how much does this cost? We could make this out of platinum, but we're not going to be able to afford that. The initial material property consideration, what's it going to do? Where is it going to live? Is it going to be in sea air? Is it going to be in space? Is it going to exist outdoors, indoors? And then the material degradation. How is it going to age? Refined material selection, you base it upon what are its mechanical properties? Like how much force does it take for it to break? How, you know, to squeeze it, to twist it, to shear it. Thermal, how well does it conduct not electricity, but conduct heat? Electromagnetic, is it chemical? Its ability to withstand different chemicals. Making a countertop, like if you cut limes or something, that's very acidic. Like what do you want to make your countertop out of? Because depending upon what sort of things are going to be on it. The mechanical properties, strength, hardness, ductility, and stiffness. These are all, we're going to get into what these specifically mean, but believe it or not, something can be very strong, but not very hard, right? Steel would be a good example. Ductility, stiffness. You can have separate, these are not linked to one another in any way. Stiffness, its ability to resist deformation. Ductility, how far you can actually stretch and mold, make different shapes with the material. Hardness, we test hardness by pushing in a point. Like you take a nail and you push it in there with the amount of force. How big of a circle or crater does it make inside of there? Strength, how much force can it hold before it breaks? So all these things are independent of one another. Thermal properties, how much heat can it hold? How much heat can it transport from point A to point B? And then does it get bigger or smaller depending upon if it heats? Maybe you're familiar with like the red ring of death back in the Xbox 360 days. This is dating myself a little bit here, but that whole happened because the thermal expansion between the different materials, when it would heat up, they would deform a different amount and they would lose contact, and then your Xbox wouldn't work. Electrical properties, does it conduct electricity? Or can you stimulate or provoke a thermodynamic response? Chemical properties. Does it rust? Oxidation and reduction. Is it toxic? You know, is it good for your body? I mean, mercury is a really good switch. You know, it's a liquid metal, but it's really toxic to people. Causes cancer. Flammability. Is this thing going to start on fire? Alternate materials. Material selection and development is currently focused on alternative materials. Fullerenes, liquid crystals, biocompatible materials. I mean, you're going to start seeing things like the straws. I mean, just in the last 5 years, I've seen straws go from plastic, and now straws are almost exclusively, when I go to restaurants, they're cardboard, because it works for that set amount of time, but then it's going to biodegrade. So, in closing, there's a lot of problems in this world that material science can figure out. Like, what are the different material properties that we're looking at inside of each thing? And we're going to get into different materials. So you're going to bring in a product, something that's got at least 4 different materials in it. So you can't use this, but here's a mechanical pencil. Here's a product. It's got a whole bunch of different materials in here for different purposes, right? There's graphite in the lead. There's metal in this thing that holds the lead. The case is made out of different types of plastic. There's an eraser on there. They all have different material properties for different purposes. So you're going to have to grab something, some product. Can't use a pencil, pen, something like that. But you're going to be looking at the different materials in there to talk about why they picked what they picked. See you later.